Hey, thanks everyone. Our next speaker is Richard Danner, who will be talking on convex geometry of building sets. Thanks.
Hello. Okay. I'm very grateful to be here with my advisor, Spencer Backman. And this is joint work with him. We're coming from the University of Vermont. So the work stems from the work of, many of you might know, Daejeon and Perchesi in 1995 on the wonderful compactification of a hyperplane arrangement. So we'll be focused in the beginning here anyways, we'll be generalizing this, but complex hyperplane arrangements whose topology is much more interesting. So you have a collection of hyperplanes. For example, the Orlik-Solomon algebra calculates the cohomology of the complement of the hyperplane arrangement. Just drew a picture just to show why the topology is a little bit more, well, much more interesting in the complex case. If you set, say, z equal to 0, if you were to do x equals 0 in the real case, for example, the fundamental group would be nearly trivial. But it's much more interesting. If we have two copies in the complex case, we already have the torus. So it's called the coordinate arrangement. There's also the braid arrangement, which is where you set the coordinates equal to each other. It's also hyperplanes. The normal vectors to these hyperplanes certainly form a vector configuration and therefore a matroid. A realizable matroid, of course. The flats of this matroid correspond to the intersections of these hyperplanes. Right? So ordered by reverse inclusion. So if we have the intersection of everything, that would be the top element, kind of our one, and we'll talk about lattices in a minute. And the empty intersection would be at the bottom. It's called a geometric lattice, right? This would be the lattice of flats. In matroid land, we call that the geometric lattice. Here's an example more generally. Some of you maybe have thought about lattice of flats of graphs, but here's the K6, the graph K6, the complete graph on 6 elements. And you can see the flats are closed in the sense that if I have 1 and 3, I have to include 6 because 6 is kind of dependent upon 1 and 3. And so that shows up over there. And for example, 1, 2, 4, we get this triangle here. So we get this lattice of flats. So Daejeon and Perchesi in their wonderful compactification, they obtained this compactification of this topological space by performing blowups along subsets of this lattice. Here's an example of a blowup. You take a place where this is not a transversal intersection, not a transversal crossing, and they blow up along, in this special case, it would just be one projective space, and the dotted line would be the normal crossing divisor. So some algebraic geometry, just doing a picture for that. This is kind of a remark. Why are we interested as combinatorialists in something like this? Well, for one, the Chow ring of the matroid generalizes the cohomology of the wonderful compactification, which has been made very popular recently. Y sub A, yeah, the wonderful compactification stratified by the irreducible components of the normal crossing divisor and their intersections. Okay, I'm going to talk about post sets in general. We kind of get the lattices here. What do we mean by products of post sets? You take two post sets and you multiply them together. If you were to impose an order relation on that, you would probably come up with the one that I didn't write the definition down for here. But you can see, yeah, you have some incomparable elements. We have irreducible elements. An element of the lattice is irreducible if you look at the interval from the bottom element, which we're writing 0 hat, all the way up to X, if that can't be decomposed as a product, we call that irreducible, if it doesn't factor. So in this seminal paper, they discussed or came up with special subsets, which they're calling building sets. They have the property that if you take any subset, any subspace, right, we're looking at vector spaces here, these hyperplane arrangements, you can express it as a direct sum if you can express it as a direct sum, so there's already kind of the sense of non-intersection, which we'll talk about later. You take a subspace and you look at all the, if it's not already in your building set, this special subset, and you look at all the maximal ones that live below it. So you're a building set if it can be expressed as a direct sum, if you have enough of these elements in your building set to form a direct sum to create the, to add up to it. Building sets are a good choice for a subset to give us the wonderful compactification. In 2004, Feichner and Kozlov, they generalized the building sets to finite meet semilattices. I should have that definition now, it's coming in a minute. Okay, so here's the definition of a building set, and you can see it's kind of complicated. Right? It's kind of messy here. We look at, again, these intervals from 0 to x, but it still has the same flavor. We've got products in place of direct sums, right? And we're looking at the x sub j. They're kind of the maximal things in this set, this building set that live below it. If you're able to write this, if for any x you're able to write this interval 0 to x as this product, then you have a building set. Messy to work with, though. Here's some examples. The irreducibles, they form a building set. And that kind of makes sense, right? You can take any element and multiply it. It's just like in number theory. Take a number and represent it as a product of irreducibles. The irreducibles in a factor tree, for example, would not be the prime numbers, but actually powers of primes, incidentally. The maximal building set, you can just take the whole lattice. You can blow up along the entire lattice. That's the maximal building set. We're basically exploring what happens in between these two extreme examples. And we'll talk about, that's basically where we're going. So this definition, here's another definition of a building set. It was equivalent, Daejeon and Perchesi had it in their paper as an equivalent definition of a building set. You look and see if, first of all, your building set has to have the irreducibles, and if you don't have the irreducibles, how are you going to, you need to be able to get everything. How are you going to arrive at an irreducible if it's not already in there? And then take any two other elements in your building set. If they have non-trivial intersection, then they're joined. For those familiar with lattices, right? We have meets and joins, so basically greatest lower bound and least upper bound. The least upper bound, the join better be in there if they have non-trivial intersection, as long as their join exists, that is. Okay, so this was generalized to arbitrary meet semilattices. So Daejeon and Perchesi, they had it for the hyperplane arrangements, but turns out to be true in general. For the Boolean lattice, this characterization is kind of lost for a little while until it was popularized by Feichner and Sternfels in 2006, and Postnikov, I think that date's wrong. I think he defined that a little bit earlier, someone might know. For the Boolean lattice. So it's the Boolean lattice specifically on elements 1 through n, where what's the join in that case? The join is just the union of subsets, right? Very specific matroid. But now it's been generalized to arbitrary meet semilattices. Closure operator on a ground set is just the map from the power set to the power set, and it has these properties, right? So the closure should be larger. In a minute, we'll have an example of matroids, an example of this. There's names for these bullet points. I didn't write them down in fancy names, but you're closed if under the closure operator, nothing happens to it, right? So sigma of A is A. If that's the case, then you have a closed set, so an element of our closure system. So that last definition that we had here, calling this the useful characterization. It's just kind of the name that we've been saying. Fechner and Sternfels used this useful characterization to show that building sets of the Boolean lattice determines a closure operator. Okay, so building sets themselves, in this specific case, form a closure operator. Is it only in that specific case? No, and that's another one of the points of this work here. So a closure operator is, if you have a set system, the closure operator is you just take all those sets that are closed, such that closed under that operator. We call that a closure system. Some examples: a matroid. Right, here's one of the cryptomorphic definitions. If you know the definition of a matroid under a closure operator, you're used to having these three, right? And then there's the fourth one. I just threw the fourth one in here. So it's already a closure system, and here's the fourth one. There's also what's called a convex geometry, right? And this is not like the study of convex geometry or anything like that. This is a specific closure system. And it has this anti-exchange property. And it's clear what this looks like. It's better to understand with the picture anyways. So you can see that if X lives inside the closure, I think I might have the X and the Y backward from the definition, excuse me. But hopefully you get the idea here. Let's say it according to the picture here, you can see that X lives inside the closure of A, which I call this, the green spot is A. If I include Y, if X lives in that closure, then Y should not live in the closure with X, right? There's this notion of convexity with this sense here. All right. Well, there's another definition due to Edelman and Jameson. You got a set system. And if you take two elements of your two sets within your set system, so two elements of the set system, subsets of some ground set, then there exists some element in A that's not in B, that if you remove E from A, it's back in the set system. Right? Yeah. So it's a equivalent definition. Not going to define antimatroids, but convex geometries are duals of antimatroids, if you're familiar with them. There's a special type of convex geometry called a supersolvable convex geometry. A supersolvable lattice was defined by Stanley in 1972. He was motivated by the study of supersolvable groups. Right? So you have a normal chain of subgroups such that the factor groups are cyclic. And he studied that in terms of, I guess you'd have, the lattice of subgroups. And this definition, you can ignore it. It's not part. It's just sort of the history of what's going on here. We're not going to get into M chains and things like that. Some of you may already work with them, but okay. In 2009, Armstrong discussed a supersolvable anti-matroid, and then Gillespie in 2020 looked at the dual of that. So convex geometries and antimatroids are dual to each other, and in the supersolvable case, and here's this. So a supersolvable convex geometry is a convex geometry, but instead of just there existing an element, you can look at the minimum one. Whenever you have the minimal element that's in A and not in B, you can remove that element, and so not just there exists this specific one, this minimal. If you remove it from the element A, you're back in the closure system. Okay, so it's closed under doing this. All right. So, turns out that the set of building sets, if you take a meet semilattice, for example, a geometric lattice, they form a convex geometry, a supersolvable convex geometry. And now you have to pick a linear extension, right? So any linear extension you want. Here's a proof by picture, essentially. So if you take X here, it's the smallest thing that's in B prime. So building sets, so I stopped using A and B, we're using B prime and B. Take the smallest thing that's in B prime, that's not in B, and we want to see that we can remove X from B prime and that we're a building set again. Well, that's where our useful characterization comes in. The useful characterization said that we can prove that something is a building set by using this useful characterization. I'm going to take two elements, any two elements in B prime minus X, because that's what I'm trying to show is a building set. So Y and Z here. I take anything, and if they have non-trivial meet, so they don't meet at 0, I need to show that their join is also in B prime minus X. And it is. They inevitably must be less than or equal to X, since X is the minimum one. We're only looking at things less than X here, so they live in there. They also live in B because X was the smallest thing that wasn't in B. So Y and Z live in there. Well, B was a building set, so their join lives back in B. And since we're in B, we're not equal to X, and therefore I took two things. They also still live in B prime because of the useful characterization again. And voila, we've proved that we can remove the smallest element that wasn't in B from B prime, and that is still a building set. So the set of all, just to reiterate, the set of all building sets, which we're denoting by blackboard bold B, right? The set of all building sets is in fact a super solvable convex geometry. Here's the exact same lattice of flats for K6, right? For the complete graph on 6 and 1. It's just the same thing we were looking at before. But now here's the lattice. So super solvable convex geometry comes with the lattice. That's what Stanley started with, and we have this lattice here. It's just ordered by inclusion. Now, I haven't specified a linear extension here, but you could certainly come up with one. Let's say the green elements means that element's not in my building set. So each one of these represents a building set. This one's the set of all irreducibles. Take a look at 1, 2, 4, right? You can't write 1, 2, 4 as a product of smaller posets. It has to look like a cube. The smallest product you can get looks like a cube. I don't have that with 1, 2, 4, so that's irreducible. So these at the bottom are the irreducibles. Here's the maximal building set, and then everything else in between. Let's look at these two. Maybe this is B prime, maybe this is B. Here's something in B prime with the right linear extension. This would be the smallest thing in B prime that's not in B. So if I remove it, since we have a convex geometry, super solvable convex geometry, if I remove this one, in this case, I get this, and again, I arrive at another building set. So here's just an example showing what's happening here. The wonderful compactification, stratified by the irreducible components of the normal crossing divisor and their intersections. It's just some algebraic geometry mumbo jumbo. So the wonderful compactification is obtained by blowing up along, if you obtain the wonderful compactification by using the maximal building set, the poset strata of these intersections coincides with the chains. Okay, so it's like indexed by the chains. More generally, however, again, we're going to be blowing up along building sets that are not the maximal building set. So more generally, we need to define a nested set. All the chains are nested, but we have more of them as well. We also include some incomparable elements. So a set of incomparable, take a subset of your building set. If you have some incomparable elements, if their join is not in the building set, they don't live in there. You can kind of think of us trying to get maximal elements below some kind of thing. As long as their join doesn't live in the building set, then we call that a nested set. So take an arbitrary building set instead of the maximum one, which gave you the poset strata via chains. Now we have the poset strata indexed by these nested sets instead. Nested sets form an abstract simplicial complex, for those familiar with that, right? Associated to the building set. For those of you that know the order complex, what's the order complex? It's the abstract simplicial complex, which is made up, the faces are made up by, are made up by chains, right? So when you take the maximal building set, we just get the order complex. So even in the case of the Boolean matroid, there are many interesting constructions happening here. Take the Boolean matroid, we can take as a building set, we can take the set of all paths. If we look at the Boolean lattice as say like the associated, the graphic matroid of the path on 10 edges here. So you can see that what's the join of 1 and 3? The join of 1 and 3 is 1, 3, right? We're just taking unions. We're in the Boolean case. Is 1, 3 a path? No. So 1 and 3 forms a nested set. And here's probably an example of where the term nested comes from. You can just see in the picture that there's this kind of upward nested thing happening here. This nested set, in this example, it's called the associahedron. So even with the Boolean matroid, it's just this very kind of seemingly maybe uninteresting matroid, we've already got a lot of interesting combinatorics happening here. Okay. The nested set, so you've got the nested set associated to the irreducibles, and take any other nested set complex, you got the nested set complex associated to the irreducibles, that's this here on the right. Any other building set is a subdivision of that. You can see that with the orange here. All right, in 2006, Ardila and Clivens defined the Bergman fan of a matroid with respect to the maximal building set. Didn't really have space here, but this is indexed by chains of flats. They're non-empty, and then the top one is not the full ground set. And you look at the cones. Chi is the indicator vector, right? So we're looking at cones of this. Here's an example for the matroid U3-4, right, where you have matroid on 4 elements, where all 3 element subsets are bases. In pink is the matroid-based polytope, and the Bergman fan is a subset of the normal fan to this. And I drew an example where we have, so therefore we have rays coming through each of the faces. This is not the whole Bergman fan. It just gets kind of becomes a mess of a picture. So I'm just looking at the portion of the Bergman fan of this case that goes through these faces here. And this is the one coming out through the triangle. So here's an example of a cone, a 2-dimensional cone. They don't get bigger than that, right? So if you go up to 3 elements, all of a sudden they span the whole space. So there's a chain, 1 inside 1, 2. More generally, Feichner and Sternfels, same year. Sternfels, I believe, was the advisor of Clivens and Ardila at the time. I could be wrong about that, I apologize. The Bergman fan of the matroid with respect to an arbitrary building set is the following collection of polyhedral cones. Instead of looking at cones, again, what do nested sets do? They generalize the order complex. They generalize chains. They have all the chains plus some other stuff. So we're looking at cones along the indicator, associated to the indicator vectors for nested sets instead of just the order complex, instead of just chains. All right. The Boolean matroid, if you have the Boolean matroid, we consider this, we call this Bergman fan the nestahedral fan. Researchers are starting to think more about Bergman fans for intermediate building sets. Right? So if you look at a lot of papers, some people don't even say it, or they say, oh, we're using the minimal building set, or we're using the maximal building set. We were very curious, like, what happens if you consider what's going on in between? Several people do consider that. For example, Braden, Huh, Mathern, Proudfoot, and Wang described the augmented Bergman fan as a subfan of the stellahedral fan. Crowley, Huh, Larson, Simpson, and Wang described the polymatroid Bergman fan as a subfan of the polypermutahedral fan. They consider non-maximal and non-minimal, maximum and minimum, excuse me, they're unique to say that. Aaron Larson described the augmented Bergman fan of a polymatroid as a subfan of the polystellahedral fan. The following is inspired by the Bergman fan constructions and a result of Montavani, Padrol, and Palau for oriented matroids. It's kind of it's sort of a corollary to the main theorem of the paper. You take a simple matroid with a lattice of flats, take an arbitrary building set, look at the Bergman fan associated to it, then there exists a nestahedral fan, right, associated to a Boolean matroid, such that the Bergman fan of this one is a subfan, lives inside of it. Sort of kind of an interesting analog of, what is it, like Cayley's theorem for groups, that every group lives inside of the permutation group. So that's it. Thank you very much.
Okay, any questions?
Sorry, this is like a rather silly question, but can you go back to the useful characterization slide? I think that was pretty early on.
That's the heart of it, so I'm glad we're looking at that.
Right. Can you give like a simplest example where this is like a better characterization than the usual definition that people like to write down for the building set?
I think the best answer is to look at this. Ooh. And then look at that. That's kind of it.
I mean, yes, this is something sensible, but okay, sure.
Yeah, there's a paper, Incidence Combinatorics, by, I believe, is it mine? Oh, stay back a little bit. Okay, by, I believe it's Feichter, Kozlov. They wrote a paper called Incidence Combinatorics, and a lot of their proofs that they do to prove things with building sets, they're just a cumbersome mess. And with this, I went through that proof by picture, but with this characterization, it's really easy. Like, oh, do they have a non-trivial meet? Oh, they do. Oh, then their join better be in there. That's it. So it's just really, it's kind of fun, as opposed to just this crazy product definition, which you have to think about stuff like that.
Thank you.
Any other questions?
Do you have any?
That's me. I can stand.
Do you have any good intuition on why building sets satisfy anti-exchange axiom?
No, I don't. That's a very interesting question, though. I intend to spend quite a bit of time with building sets. There's a lot to do with this now. I appreciate that question. It's very interesting. I do not.
Okay, let's thank our speaker again.